All right, so for the first question, we have a very long, solid, non-conducting cylinder of radius r with a positive charge of uniform volume density rho, and this is just a section of the cylinder far from its ends. And we're going to let r represent the radial distance from the axis, and we just got to express everything in terms of r, 2 r's, rho, and any fundamental constants. Using Gauss's law, derive an expression for the magnitude of electric field at a radius r and draw an appropriate Gaussian surface. So the radius r is going to be less than the radius of the cylinder. So if we're going to draw it, you could kind of draw it like this, right? We have, oh, that's text. Yeah, something like that. And then we can kind of draw, it's luckily with Notability, you can straighten it out. But you can draw it like that. And that's a cylinder with a radius r, which is less than the actual radius of the cylinder. So with this Gaussian surface, right, when we're doing Gauss's law, we always write that the magnetic flux through that surface is going to equal the total enclosed charge over epsilon naught. So we chose a cylinder because it's going to have that symmetry, so we can take E out of that integral. In other words, at every point on the area of that cylinder, the electric field is the same. So the Q enclosed, well, we know that rho is going to equal the total charge over the total volume. So really, for the charge enclosed, it's going to equal, well, rho is still the charge enclosed over the volume enclosed because it's uniform. So it's going to equal rho times volume enclosed over epsilon naught. E is what we're solving for, the electric field. This is part A. And the area is 2 pi RL. We're using little r here because the flux through the Gaussian surface is the area we're referring to, through that Gaussian surface of radius little r. And it's going to equal rho times volume enclosed. That is for the Gaussian surface because that's enclosing the charge. So it's what is it, pi r squared times L, remember little r again, over epsilon naught. So E is going to equal, we're just dividing by 2 pi RL. So pi's cancel, one of the r's cancel, the l's drop, so you get rho r, oops, sorry about that, over 2 epsilon naught. And let me just have the copy when I did this myself. I think that's what I got. But yeah, there you go. That's going to be the Gauss's law problem. And let me just really quickly double check that is correct. Sorry about that. I'm sorry for the precious time being consumed here. We only got 45 minutes. Oh no. Yeah, and I think that would indeed be correct. Yep. Okay, so the next part of the question asks, using Gauss's law, derive an expression for the magnitude of the electric field at a radius r is greater than r. So we don't have to draw. We don't have to draw, and I probably wouldn't draw it in the actual exam. Don't draw it here because it might throw them off. But if I am gonna think about, well, when is the radial axis gonna be greater than the actual radius? It's gonna be something like this, right? So if we go back and do our Gauss's law again, write the same. Actually, I don't know. I'll always write like the Gauss's law thing, like the law or like the equation, because you probably will get points for that. So once again, we're using a cylinder, so we can use symmetry, EA. Now, Q enclosed, you might be tempted, all right? Rho times volume enclosed, and you're going to go through the same steps of like, okay, well, E this time, we're using, once again, the surface area of the Gaussian surface, so 2 pi little RL. You might be tempted to do the same thing, pi little r squared L. But the volume enclosed this time is not the volume of the Gaussian surface. How do I know that? Because, hey, there's not charge filled through this entire large Gaussian surface. It's just the charge of the cylinder. So this is going to actually be the total volume of the cylinder, not the total volume of the Gaussian surface. So it's going to be big R. And now we just divide. L's drop, pi's drop, and we get E is equal to rho R squared over 2R epsilon naught, right? That looks right. So yeah, box your answers, I guess, too. Next part, we're gonna sketch the electric field as a function of the radial distance and explicitly label any intercepts, asymptotes, all that good stuff. So our first function was a linear relationship, right? E and then R, it's linear. So we can make it linear like so. And then we have it being more like a, not exponential, but like a rational function, right? Because after it's larger than R, the distance from the axis little r, that's in the denominator. So as you get farther away, your electric field gets weaker. Hopefully that kind of makes sense, right? And then when you're inside of the field with all the charge, as you get closer to the outer edge, if you will, right? As you're going closer this way, you're getting more and more charge. There's like more and more electric field. So yeah, and we can just label this maximum as rho R over 2 epsilon, right? That's the maximum you're gonna get at that point, and then it's just gonna be decreasing from there. Derive an expression for the magnitude of the potential difference between R equals 0 and R equals R. So for this, we're going to say that we know that E is equal to dV dr, or dV is going to equal E dr. So if we're going to integrate this, right, to find the total, we get that V is going to equal E. So E as a function of R, well, we could just use, since we're going from 0 to R, right, we can just use this rho R over 2 epsilon naught dr. This isn't too bad to evaluate. Just use your proper bounds. We're going from 0 to R. V is going to equal, now we're doing rho over 2 epsilon naught, and it's just integrating R, right? Because when you pull out the constants, it's just R constants. Nice. Constants, when you pull out the constants, it's just R dr. So we're doing 1/2. When you evaluate that integral, it becomes 1/2 R squared. Going from 0 to R, and that leaves us with V equals 1/4 rho R squared over 2, no, not 2, because I took that 1/2, so over epsilon naught. Rho R squared over 4 epsilon naught, in other words. So there you go. Is the potential higher at R equals 0 or R equals R? It's actually higher at R equals 0. Here's why. So think about this. If you had, now obviously it's a solid, so it's not going to quite work like this, but if you had like an electric field that was like this, right? If you had an electric field that got bigger as you got closer to R, what you're going to find is that if you put a positive charge at the middle of that, and at R equals 0, it's going to go to the outer rim, right? Because there's a bunch of electric field pointing radially outward, so it's going to follow that. And when you get at R equals R, it's going to keep going, right? Like our electric field looks like, if this was a front view, it looks like this, right? So in no world is a positive at R equals R going to go to the middle, right? It's not. It always goes from high to low potential. So in that case, if you put it at the middle and it goes to the rim, that means it starts at high potential and it's gaining kinetic energy as it goes to the rim. It's losing potential. The potential is higher at R equals 0. There's a way you can think about it mathematically using this integral, because we avoided a negative sign because we were just worried about like magnitude. But you can also think about it mathematically if you'd like. Part E, the non-conducting cylinder is replaced with a conducting cylinder of the same shape and same linear charge density. On the axis below, sketch the electric field as a function of R for R equals 0, R equals 2R. So here's the deal, right? If you think about conducting, so if we had the same thing, but if you had a conducting cylinder, all the charge is like on the surface, right? Because it's a conductor, right? You're never gonna have charge that's just in the middle of it. Charge wants to like spread out naturally. It's gonna be all over the surface. That's why it has a linear charge density, which is gonna equal Q over L. So now, from 0 to R, since there's no charge in the middle, if you do your Gauss's law, the charge enclosed will always be 0. There's no electric field from 0 to R. And then, when you go from R to R, there's going to be some, electric field, and then as you get far away, it gets weaker. And you can derive that. I think it would be E equals lambda over 2 pi r epsilon naught. So it'd be rational. And I got this from Gauss's law. I believe you only got 2 points from this. If you did, according to the scoring guideline, you got a point if you had the 0 to R and if you had this curve that's like concave or up or whatever, concave up and decreasing. But it also says explicitly label any intercepts, asymptotes, maximum or minima with numerical values. So you would think that you would put like E equals lambda over 2 pi r epsilon naught, but they don't give us lambda, so do you do Q over L? And it's like, well, they don't give us charge either. They give us rho, so I guess you would do, oh, actually that makes sense. I guess if you do Q over L, the charge would just be, well, I don't know. They didn't talk about giving you any points for labeling any maxima, so I guess it's not a big deal. I don't know. We can move on to the next one. That one's kind of weird. In the lab, you set up a circuit. It contains a capacitor C, a resistor R, a switch S, and a power supply, as shown in the diagram above. The capacitor is initially uncharged. The switch, which is initially open, can be moved to positions A or B. Hopefully that wasn't too fast. Just trying to go fast here. Indicate the position to which the switch should be moved to charge the capacitor. Hopefully this is kind of like a, well, duh kind of thing. Like, if it was at A, well, there's no current at all because this capacitor is not charged. So you get like this kind of a loop, but there's no current flowing through it. In order to get current at all to charge this capacitor, you got to flip it to B so you get current. So it would be B. Hopefully that's not like too crazy. On the diagram, draw a voltmeter that is properly connected to the circuit in a manner that will allow the voltage to be measured across the capacitor. If you know anything about voltmeters, you always want to do it in parallel. Because if you remember your rules, the voltage across each branch of a parallel like circuit is the same. Whatever voltage is across here, it's going to equal the voltage across here. You don't do it in series. That would be different. That would be for an ammeter because current is the same in a series like thing. Okay, after a long time, you move the switch to discharge the capacitor and your lab partner starts a stopwatch. You collect the following measurements of the voltage across the capacitor at various times. You wish to determine the time constant from the slope of the linear graph. Indicate two quantities you would plot above to maintain a linear graph. So for this one, yeah, I'll just do it here. You kind of have to like know your equations, right? So if you think about, okay, well, voltage as a function of time. Let's start here. Q as a function of time. This is the one I have memorized real well. It's going to equal Q max times 1 minus e to the negative t over RC. And we're trying to get a slope that gets you RC. But this is charge. We need voltage. So if you think about capacitance, C equals Q over V. So V is going to equal Q over C. I just divide everything by C. So now I get V as a function of time, which is going to equal... Oh, this is completely wrong. I'm so sorry. I just realized this. This would be like this. It's a decay. This is oh my god, I am so sorry. Just void the 1 minus. It's Q max times e to the negative t over RC. That's for discharging, you're losing charge, so you're going to get that decay function. V as a function of t will get Q over C times the same, like e negative t over RC. I just divide Q max by C, which will just equal the EMF, or the initial voltage. Like, yes, that would be the voltage of the battery. So in order to yield in order to yield this, there's a couple ways you can do it. I would just ln both sides. The reason I ln both sides is, first of all, I get ln V. I'm trying to get rid of the E, that's the main thing. So if I ln V, I can do ln V initial. This is my log properties, ln V initial plus ln E to the negative t over RC. When you do ln of a product, you can also split it up. And that's real nice because I get ln V is just equal to, the ln cancels out the E. I get ln V initial, which is my y-intercept, minus t over RC. Slope would then be RC. So that's how I get a linear graph. I need to natural log the voltage. So that would still be in volts, I believe, right? Because this would have units of nothing, because this is seconds over seconds. So I think it would still be volts. Hopefully, we'll see. They said use units, but then you never got points for units. So, and they don't even use units in the example. So who really cares? Let's ln everything. This will take a second. ln 252, 5.53. ln 74, 4.304. Or I'll just do 4.30, why not? ln 33, 3.50. Let's do that, 50. Because it's 496. ln 10, that would be 2.3. I have like a bootleg Apple Pencil, so it's really crappy sometimes. ln 6, 1.79. I don't need to do anything to t. That's already set. Let's graph the data. So you have to scale it, and I kind of hate scaling. You know, I guess I'm not an experimentalist by heart. We're doing ln V versus t. At least that's what I want to do. Like, that makes the most sense to me. At a certain time, I can find the natural log of the voltage. I don't, like, you could do like ln V, like t as a function of ln V, but in my head that doesn't make sense, because it's like the natural log of the voltage does not affect the time. The time is what's changing. The natural log is what I'm measuring, but I guess it'll be easier to find the slope that way, but who cares? ln V versus t. So my time is going to be 6, 18, 30, 42, 54. I can honestly, what app did I have open? I just that. So we could just, I think this just plans out. It's like each tick being 1 second. So I have 6 right there. I have 18 right here, right? Because this is 10. And then the next time, it's just adding 12, right? So 30. Oh, that won't fit at all. That fit? And then I have 42. Yeah, no, that won't fit. There's no way on earth that fits. So I think I have to do it like this. So 2, 4, 6, 10. This would be 18. This would be 30. This would be 42. And then the next one is 54, right? So this would be 54. That's a pretty nice scale. Yeah. So now I just do the same thing for natural log, and I think it also works out well, because this could be like 1, 2, 3, 4, 5, 6, and I can use my points like 0.2, 0.4. So start at 6, I have 5.53. So 5 point, I guess right around here. 18, so at 18 it would be 4.30. So that's a little more than 4.2, so kind of in between 4.2 or 4.2 and 4.4. 3.5 would be for 30, so that's like in between 3.4 and 3.6. 42 is 2.3. So that would be in between 2.2 and 2.4. And then the last one is going to be 54, which is 1.79, which is pretty much perfectly at our increment. So I'll do it right below. Make a line of best fit. So if I'm thinking about this, it would kind of be, I literally turn around my iPad just so I can kind of get an idea. I think it would be like this, right? Yeah, kind of like that, I think would be good. Yeah, I mean, that seems about right. So, now, from your line, obtain the value of the time constant tau. So, we talked about how the slope, right, this would be, if you think about y equals mx plus b, this is b, the y-intercept, x is our t, so the m would be negative 1 over rc. So, with that, we know slope equals negative 1 over rc, which is just tau, so 1 over rc, so slope is equal to negative 1 over tau. Use the line of best fit. I actually got, I think, no points from D. Yeah, I think part D is 2 points, and I didn't get any points because I didn't use the line of best fit. I used the actual data points, but you're not supposed to do that. Like, no duh, I should have known that. So for my line of best fit, I guess this is a clean line or a clean point to use. What's another clean point? I guess right here. So slope is gonna be, so this would be 56, and so let's use this. So the ln1 is 1 minus, so I'm using y2 minus y1 over x2 minus x1. 1 minus 4 over 56 minus 20 equals negative 1 over tau. Might as well take the reciprocal right here. 56 minus 20 is 36. 1 minus 4 is equal to negative 3, so that's equal to negative 1 over tau. And I get 12 is equal to tau. So that's my time constant, 12 seconds. It's pretty large time constant. You're going to see it right here. In the experiment, the capacitor 1.5 microfarads of capacitance. Calculate an experimental value of R. So for here, you could say that, okay, well, tau is equal to RC, so 12 seconds is equal to R times 1.5 times 10 to the negative 60 farads. And I get R if you divide 12 by the capacitance. Let me just do my calculator here. 12 divided by 1.5 times 10 to the negative 6. Delete. I get 8,000 something. Not 8,000. It's 8,1,2,3,1. So 8 million ohms. Goodness me. Which makes sense. That's a pretty large time constant. Like 12 seconds to get to 63%, or like to have consumed 36, or not consumed, but for your current to have decreased by like 36%, or your charge or whatever, that's crazy. That's pretty nuts. That's pretty nuts. So kind of crazy. On the axis of part C, use a dashed line to sketch a possible graph if the capacitance was greater. So hopefully you can kind of see immediately, greater capacitance leads to greater time constant. And we said that, hey, time constant is the reciprocal. So greater time constant would lead to a slower slope, right? Because if I increase tau, my slope goes down. So that would be more shallow of a slope. So kind of like this. Same y-intercept though, because I start at the same initial voltage or whatever. So for my justification, I would just kind of say slope is reciprocal, or I guess negative reciprocal of time constant, increasing the capacitance increases my tau, so slope gets a little more shallow. I think that's fine. It just said a valid justification, like based off your stuff, whatever. So glad I didn't use this extra page I created. Let's just move on. Oh man, I don't even need this extra page because it gives me actually a good amount of space. Maybe I should just not do that again. Figure above shows a circular loop of area quarter of a meter squared and resistance 12 ohms that lies in the plane of the page. Magnetic field of magnitude B directed into the page exists in the area of the loop. The field varies with time t as shown in the graph below. Wow! Look at this graph. Pretty nice graph. Derive an expression for the magnetic field. I'm going to say magnetic field instead of magnitude like all the time now. Derive an expression for the magnitude of the induced EMF in the loop as a function of time for the interval t equals 0 seconds to t equals 8 seconds. So for this graph, first of all, you should write Faraday's law, because remember, change in flux creates, change in magnetic flux creates an induced EMF. So in the induced EMF, if I'm looking at magnitude, it just equals the derivative of flux with respect to time. What? I don't even know what I'm saying. With respect to time. I think I was trying to confuse like change in flux and change in time, and I just combined them. So the derivative of flux, like the change in flux per time. So if I take the derivative, I'm really taking the derivative of BA, right? The product, and no cosine theta because they're like parallel, like the area vector and flux. So I'm doing A. I can pull that out because that's a constant. Otherwise, I would need to do product rule. A times the derivative of B. So 0.25 multiplied by dB dt, which is just that function they gave us. So d of 1.8 times e to the negative 0.05 t. If I'm taking the derivative of that, I'm going to do my chain rule. So I can pull out the 1.8, and I'm also pulling out the negative 0.05 t. Yes, that's what I'm doing. And then you would do, once again, e to the negative 0.05 t because of chain rule, right? Why did I put a t in there? I'm so silly. Why did I put a t in there? I went on autopilot for a second thinking about the negative sign, and then I just completely forgot I added a t there. If you multiply those, you get the induced EMF as a function of time is going to equal, multiply those. You can, I think, void the negative, or I don't know why I'm saying void. You can, like, let go of the negative because, like, that deals with the direction, because it's like negative, so that's probably, like, something counterclockwise or clockwise, so don't worry about it, I guess. 0.05. So you get 0.025 times e to the negative 0.05 t. Derivative rules, that's the main thing. And this function makes sense, right? The magnetic field is changing less and less as you approach this flat line. So your induced EMF is going to decay. Calculate the magnitude of the induced current at time equals 4. So we're given the resistance of this loop, right? Yeah, so we know from Ohm's law, one of the greatest laws ever made, I guess, I don't know, I is equal to V over R. So the induced EMF at T equals 4 over the resistance. That's the main thing. 0.0225 times E times negative 0.05 times 4 over 12 ohms. That's the main thing. So I'm going to say, multiply that by E to the negative 0.05 times 4. You get a really small number, divide that by 12, you're going to get 1.54, if you think about rounding, times, or I guess 10 to the negative 3, which is just milli, so milliamps. Awesome. Awesome sauce. So we're going to sketch a graph of the induced current from time t 0 to t to 18, assuming that counterclockwise is positive current. So for this, this is really just going to be like this function. I guess I can kind of create a copy. So how do I paste? So this is just going to be like kind of not proportional, but like, I guess, yeah, kind of proportional to this, because the I is a function of time. It's just going to be the voltage divided by the resistance. So it's just going to be this. So it's going to follow the same shapes. So, but now the main thing, is it clockwise or counterclockwise? Well, during this entire time, the magnetic field is either decreasing or it's like staying the same. So if my magnetic field is decreasing, it's getting less. So it's like, this is like Lenz's law, like 3-step guide. I got this from Mr. Gustin. It's actually really good. So if your magnetic field is decreasing, okay, so first identify the change. What's the change? The magnetic field is decreasing with less coming into the page. So now what's the opposite of that? You need more going into the page to counteract that. How do you get more? Well, you would need clockwise current. So clockwise current will get more into the page, so everything is going to be either clockwise or there's going to be no current. So from negative 8 to, or from 0 to negative 8, nice. From 0 to 8, it's going to look like this. From 0 to 12, it's going to be 0. How do I know it's 0? Well, there's no change in magnetic flux. The magnetic field stays the same, so there's no more induced current. From 12 to 16, it's gonna be like a constant current. Why? Because the magnetic flux is changing at a constant rate. And it's gonna still be clockwise because it's still decreasing. And then we have from 16 to 18, there's no current because there's no change in flux. Not because it's 0, but because there's no change in flux. So for the time interval 12 to 16, justify direction of the current you have indicated in your graph. So what I would say is kind of like the change in magnetic field is decreasing whilst directed into the page. So the current will induce a magnetic field to oppose that change by Lenz's law. To do so, current must be clockwise in direction for a magnetic field induced into the page. Calculate the total energy dissipated in the loop during the first 8 seconds shown. You can use current, but it might just be easier to do power in terms of voltage. Why am I even talking about power? Well, hey, power is equal to dE dt. Oh my gosh, this pencil is killing me. So P dt is equal to the dE's, the small amount of energy dissipated. If you integrate, you get that the total energy will be that integral. So I'm going to do V squared over R. And this will be in turn with respect to time. So I'm looking at the first 8 seconds, 0 to 8. So I can pull out the 1 over R, which is just 1 over 12 ohms, times the integral of what's the integral? Oh, why did I say what's the integral? I meant what's the voltage? It's 0.0225 times e to the negative 0.05 t squared dt. Should I do it the shortcut way with my calculator, or should I show? Excuse me. I'll show you how to do it, like just how to evaluate the integral, because maybe not everyone knows how to use a calculator, but I feel like also calculator makes it a little bit easier. If you know how to use your calculator, you can use it. I would search up how to evaluate integrals on a TI-84 calculator. Just makes it a little bit easier, but might as well show you in case you were curious. So when I'm squaring the voltage, I'm squaring the 0.0225 stuff, and I'm squaring the exponential, which just, when you think about your exponential properties, that's the same as just doing -2 times 0.05 t dt. So 1 over 12 ohms times, now I'm pulling out the 0.025 squared. So I can just kind of write this as 0.0225 squared times that integral 0 to 8. E to the -2 times 0.05 is -0.1 t dt. So if you think about that, 0.1, when you do your reverse chain rule or your U sub or however you want to think about this, you're doing 1 over -0.1 times e to the negative 0.1 t. And when you take the derivative again, that -0.1 will cancel out the 1 over -0.1. So then you get your original little thing, your original function, your integrand, or I think that's what it's called. I'm just going to evaluate the 0.025 instead of squaring it each time. Divide that by 12. You get some really small number, 4.2 times 10 to the -5. All right, let's evaluate this. 1 over -0.1. Don't worry about the negative. You'll see. I was kind of thrown off by like the negative. Wait, how can you get negative energy? -0.1 times 8 minus -1 over 0.1 times e to the 0, right? Because when you're doing 0 times this, it's just to the 0. Let's evaluate that real quick. If you just do e, so you can like factor out the -1 over 0.1, which I think is just -10. So I don't know why I'm like making it, or why I'm like just writing that out. E to the -0.1 times 8 minus e to the 0. That's just gonna be a negative number. So when you multiply that by -10, you get you get a positive number, and multiply that by the 4.2 times 10 to the 5th, you get the total energy dissipated is going to be 2.32 times 10 to the -4th joules. Not a whole lot of energy dissipated, but there you go. And once again, so glad I didn't use that. Hopefully this video was helpful in some way. If you tried this one out, or if you just want to see, I guess, how I think through things, there you go. Thank you for watching.